Right, so let's quickly look at the idea of intermolecular forces. So I'm going to try and look at the entire theme's work in one, and ways that how we need to look at intermolecular forces, what they are, how do we classify them, and why are they important. Now, the main idea is that you essentially get all of them are called van der Waals forces. So anything called a van der Waals force means that how do molecules interact with one another? And these interactions can, of course, be attractive or repulsive. And now in gas phase, that doesn't really make much of a difference. Gases are very disordered, very unstructured, so they don't really interact that much with one another. But once we get to the liquid and the solid phases, then it starts becoming much more prominent. What are the interactions between molecules and not just their bonding energies? So we need to know then what happens with the attractive and repulsive forces that they experience. Why does something want to become a liquid and then even further want to become a solid, or other way around? So things with permanent dipoles, so in other words, a molecule that has a strong electronegative element and then ones that are more electropositive interact via something called dipole-dipole forces. So look at that. You can also then, if you have one molecule, if you mix molecules where you have a dipole and it can induce a dipole in another one, you get dipole-induced dipole forces. They're also called Debye forces. And of course, you can get induced dipole forces. So that is for non-polar. So you can remember polar molecules, when you have only them, it's dipole-dipole. If it's a mixture of polar and non-polar, then you have dipole, induced dipole. And if you have non-polar molecules, you'll have a situation of induced dipole forces, also called London dispersion forces. And the reason why these forces are important to look at is because they relate to the melting point, the boiling point, the energy needed to convert substances, the solubility of a liquid, a gas, or a solid in solvents. And it can even be biologically important. So there's a lot of importance in why things like to be grouped together as is, so meaning a solid, a liquid, a gas, what's happening there, and so on. So we'll work through these options, or the meaning the dipole-dipole forces, the Debye, the London. We'll work through all of them and see what are the general rules and qualities of them. Right. So let's start with molecules with a permanent dipole. So these, of course, are going to interact with dipole-dipole forces in some kind of manner. And where we place ions in them, there's going to be some situation where if you have a molecule with a dipole, it's going to favor a specific kind of charge. So the basic example that's always used is, let's say, for example, you have sodium chloride. And if you dissolve sodium chloride in water, you'll have a sodium ion. And of course, it's in water, so you'll have water around it, usually in a hexagonal or six-membered way. So, but I'm just going to draw four of them. So you'll have a situation something like this. The orientations are not going to be exactly correct, but you will get the idea across. So there's going to be some way the water orientates itself. And the reason is because, remember, water is polar. So it means one part of the water molecule is slightly positive and the other part is slightly negative. Right, so the hydrogens are slightly positive and the oxygen is slightly negative. And because the sodium has a positive charge, the negative side of the water will automatically want to orientate itself towards the sodium, whereas the chlorines are going to pack in the positive part. So there's going to be chlorines all around here. And of course, then you have an iterative structure because then you'll have water again and sodiums and so forth and so forth. So these are what we call ion-dipole forces. So you have an ion like sodium and you have a dipole molecule or a polar molecule like water, and you create an ion-dipole force. Now this force is dependent on a few factors. The first is the distance between the ion and the dipole. So in other words, this let's use that color, this distance here. So how far is the sodium plus away from the oxygen minus? It's also dependent on what is the charge of the ion. So is it sodium 1 plus, 2 plus, 3 plus, 4 plus, 5 plus? And you can think for yourself, the stronger or the larger that ion charge is, the more positive or the more negative it is, the more interaction it will have with the dipole. It's like a magnet. The higher the charge, meaning more positive or more negative, it will have a stronger attraction. It becomes a stronger magnet to the electrons or the positive charge in a molecule to attract that. And it, of course, also depends on the dipole, the magnitude of the dipole of the molecule. So if you have a molecule that is extremely polar, then of course it also would be more, or you can easily rationalize the idea that you will have a side that is very negative and a side that's very positive. So all of these tell you essentially, if the things are closer together, they'll have a stronger interaction. If one of them is more negative or more positive, they'll have a stronger interaction. That's basically what these rules tell you. And the way we can see this is by looking at the heat of solvation. So the solvation enthalpy is sometimes called the heat of hydration. And this is also dependent on the ions in the sense that if the ion obeys these laws above, so depending on the distances, the charges on the ions, the charges or the magnitude of the dipoles, they affect how much energy is released when that salt is dissolved in the solvent. So there's a few other ones that also come in. So as the size of the ion increases, the magnitude of the enthalpy decreases. And what that relates to is if the size of the ion increases, it means the distance between the ion and the dipole also increases. And hence there's a weaker attraction. And so there's not going to be a lot of energy released when this salt or whatever is dissolved. And the opposite thing is as the charge of the ion increases, the magnitude of the enthalpy increases. So once again, if you have more magnitude in charge, so more negative or more positive, the ion charge or the ion dipole interaction is going to be stronger. So you'll also have an increase in enthalpy. So let's try and put that into perspective. So we are told to explain why is the enthalpy of hydration of sodium ions, cesium ions, and magnesium ions, why do they differ so much? And in fact, why is this specific trend to them? So let's first place them in terms of size. Let's ion size. Ion size. Well, the smallest ion here is magnesium. It's 2 plus. It's smaller than sodium, and sodium is smaller than the cesium plus. In fact, the values are, just for interest, 79 picometer. Its radius is 79 picometer. This one is 98 picometer. And this one is 169 picometer. Right. And we can also write the enthalpy. So the magnesium one is minus 1922. This one is minus 405 and minus 263. So why is it that the cesium's enthalpy is the most positive and the magnesium's is the most negative? Well, the first and obvious one is the magnesium has a higher charge, so it has a larger magnitude of charge. So the first one is that's because is this one because magnesium 2 plus has a higher charge than either sodium or cesium. So hence it will have a larger enthalpy of hydration, a larger magnitude, and hence what it actually means that it gives off more energy. It's more energy favored for the system dissolve. It's very exothermic. Not that all exothermic reactions are spontaneous, but general indication is. And then, why specifically sodium has a larger enthalpy of solvation compared to cesium? The reason in this case is the size. So, I mean, magnesium outweighs in all options, so it's the +2 and it's the smallest, but the sodium is smaller than the cesium. And that means because sodium um, uh, distance, let me just put it like this. Sodium is smaller than cesium. The distance between the water dipole and the charge is smaller. Right. So essentially in this thing, what the distance means is that in the cesium case, maybe let's try and draw that, qualitatively draw that. So in the sodium plus case, you can think of this ion like that, and the cesium plus case, it's something like that. So the water is still on the edge here. This is where the water sits. And in this case, that's also where the water sits. But in this case, it is further away from the positive core than what it is here. You see, those two distances differ. And if you have something closer to a positive charge, the interaction is much stronger than it is far away. And what does the enthalpy of solvation indicate? Well, it indicates the way of exothermically, if we dissolve the salt, there's heat released, but in the opposite way, it also tells us then how much energy is required to remove the salt again, or remove the ions. And in this case, it makes sense how closer your dipole is to your ion, the more energy you will need to remove them because they're very closely related. Whereas if it's like a far along family, it's very far removed from the ion core, then you should be, in principle, easy to remove the ion from the water without using too much energy. Okay. As well as if it's very close and the charge is high, then you're really going to struggle to remove it. Okay, so that's why it's magnesium, sodium, and cesium. Not really a typical question. This is not like an exam question. It's more you need to understand what the things mean, kind of thing, recognize them in other sections. Right. So now let's look at, so that was ions with dipole moments. The only things that we can now get are we will look at molecules. So if you have two polar molecules, a non-polar molecule and a polar molecule, or two non-polar molecules, what do you call those interactions? So first, if you have a polar and a polar molecule, so in other words, when a polar molecule encounters another polar molecule, we call it dipole-dipole interaction. And why is that? It is because a polar molecule will always split into a positive side and a negative, well, I say split, but meaning it will have a more positive side and a more negative side. And these molecules can then orientate themselves in a manner where the positive side of the one connects to the negative side of the other. And then it's almost like a plus minus, plus minus, plus minus way of orientating. So these forces are kind of strong. They're not extremely strong, but they are stronger than some of the other forces. So, for example, because they are stronger, they lead to higher boiling points, higher melting points of substances, and hence also larger enthalpies of vaporization, for example. So, in this table, we can see we always try to compare things of equal molar mass. So, if we compare N2 with CO2 or with CO, we see that both of them, right? So this is going to be N triple bond N, and this is C triple bond O. They're similar in molar mass, they're similar in structure, but this one is polar, so it has a dipole moment. This one does not have a dipole moment. It has no dipole moment. And so that's the only difference between them. Their molar masses are the same. They have the same form. They're a linear molecule. But we see there is an increase in the boiling point. So meaning the CO has a slightly higher boiling point than what the N2 has. It also has a slightly higher enthalpy of vaporization, meaning we will need more energy to vaporize this molecule or a compound, some molecular compound of CO versus N2. And you see that trend throughout. So the one that's perhaps easier to see is the bromine. So bromine and ICI, both of them linear, both of them similar molecular mass, but you can see the boiling points differ quite intensely. And in fact, this one, we don't even know what the enthalpy of vaporization is of it. So that's the general idea. If there's something has a dipole-dipole interaction, it's a strong interaction that two molecules can have. But what's the requirement? There needs to be two polar molecules interacting with one another. Like I said, so things that are influenced by intermolecular forces are, of course, the boiling point, the melting point, the heat of vaporization, the heat of anything really that you want to make a phase change or you want to change something of the substance. These forces will have an influence. But one of the interesting ones that it has, well, not interesting, just maybe explanation, is that in terms of the solubility, so a polar molecule will not dissolve in a non-polar molecule. Well, not fully. That's actually, they might solivate to an extent, but the general rule is like dissolves like. So a polar molecule will dissolve a polar molecule, and a non-polar molecule will dissolve a non-polar molecule. It's not likely that you'll have a polar molecule that dissolves a non-polar molecule. So essentially, what we take here is that polar goes with polar and non-polar goes with non-polar. So if you're asked to determine whether or not CO is going to dissolve preferentially in water or in bromine, you'll say, well, CO is a polar molecule, and water is a polar molecule, bromine is a non-polar molecule, so it will preferentially solivate in the water. Okay. A specific, well, not a specific type, but an important type of intermolecular interaction is when you have a nitrogen, an oxygen, or a fluorine with hydrogen. Okay. And these are able to form something called a hydrogen bond. So if you have F and H, or you have O and H, or you have N and H, then these molecules that have that kind of polar bond, because remember, whatever this thing is to hydrogen is going to be more negative than what hydrogen is. Hydrogen is always going to be positive. It allows for additional hydrogen interaction with that species. So the other part of the molecule that also has an H and an N will be able to interact with one another. And we normally indicate this with little dots. So that black line there is not right, but you have little dots to indicate that there's no formal bond, but there's a very strong interaction there. And the reason for that is if you think about hydrogen and oxygen's bond, the oxygen will carry like 90% of the electron density. The hydrogen is almost like a proton. So these kind of compounds have a high electronegativity difference, and that means you can almost start to approximate them as there's a positive charge and there's a negative charge, so almost ionic, but they're not. They're still bonded together. There's still a formal bond between these two species. And the effect on the properties then are that if we look at, for example, the halides, so hydrogen fluoride, hydrogen chloride, hydrogen bromide, hydrogen iodide, so these are the ones that I'm looking at. Hydrogen fluoride, for some reason, has an immensely high boiling point compared to its other halide companions. So And why is that? And that's because of these hydrogen bonds that appear in these molecules. The same with water. Water, compared to everything that goes down in the group of waters, remember there's going to be oxygen, sulfur, selenium, tellurium. Then you get the halides. So the halides are F, B, Cl, Br, I. And of course the nitrogen group, so nitrogen, phosphorus, and then antimony. So in those groups, for some reason, the ones here at the top, when they're bonded with hydrogen, have higher boiling points than the rest. Where the trend, or the, what do you call it, the trend falls apart is with carbon. So the group of carbon, selenium, germanium, and tin does not show that trend. You can see here. Here there's a simple increase in boiling point with molar mass, because that's also something that happens. The higher the molar mass of something, the more energy it would require to boil. But with these, we see, even though there's a low molar mass, the ones that contain oxygen, fluorine, and nitrogen, they have a tendency to have a higher boiling point than expected, essentially meaning they don't just go in a straight line like the ones for carbon's group does. They start high and then they all of a sudden fall off and then they go back. And that's because of these things called hydrogen bonding interactions. So hydrogen bonding is a specific type of intermolecular interaction that plays a large part in the properties of substances. And I mentioned it now that you must essentially see this bond of H to X. You must almost see it as it's a positive charge and it's a negative charge, because that explains why this bond is so polarized and causes so much effect on its physical properties, because it's not like the other compounds that is almost, like if you have a carbon to an H, and you would say, yeah, I mean, the carbon is going to be slightly negative and the hydrogen is going to be slightly positive, but they share their electrons quite well. In terms of the ones that contain fluorine, oxygen, and nitrogen, it's almost like a complete split. So if you think of it like that, which one is going to cause the bigger interactions? The one, of course, that has the complete split. And that's exactly what we see. So these molecules then allow for this dot, dot, dot notation. So this hydrogen interacts with this fluorine and is formally bonded to another one. Some people even argue that they are formal bonds, but we stay with this for the moment. So like I say here, hydrogen bonding has important implications for any property of a compound influenced by intermolecular forces. So, for example, it's responsible for the unique properties of water. Water is a fascinating species because it has because of its hydrogen bonding network, it behaves completely out of place, sort of for something of its small molar mass. But I've written a little section for you, which you can go read, and you can delve into that. Anyway, so what is the effect of a hydrogen bond? We're told that we have two species which have the same number of hydrogens, same number of carbons, um, and the same number of oxygens. But their structures differ in that the ethanol has an H3C bonded to a CH2 bonded to an O and an H. And it has a boiling point equal to, what is the boiling point given? Well, it doesn't say, but it says ethanol and dimethyl ether have the same molecular formula but different arrangement. I predict which of these has the higher boiling point. So we actually want to know the boiling point. And this is H3CO CH3, a boiling point. You can go look up those boiling points. I'm quite sure it will be illustrative of what I'm telling here. Diethyl ether, I think, boils at about 40 degrees Celsius, and ethanol, 62 degrees Celsius. That's really a guess. I'm not sure. Okay, but then the point is, which one will have the higher boiling point? And why do we say that? So what we need to identify is what are the types of forces that are going to be present in them. So both of these molecules are polar. So this one is polar, right? Because there's an oxygen. So if something has oxygen, it's bound to have a dipole moment. And this one the same. The dipole moment of this one is just towards the oxygen. So it's also polar. Um, So what is the thing that differentiates between them? The thing that differentiates between them is the fact that we have the presence of an OH bond here, and there's no OH bond in the other one. So we have here what we call the polar OH bond. And because of that, we have then hydrogen bonding. Here we have carbon bonded to oxygen. So therefore, there is no polar OH bond. So there is no hydrogen bonding. And that means ultimately that the ethanol boiling point will be higher. And it's simply because of the presence of a hydrogen bond. So you can see what the effect is on the physical property, like the boiling point, of hydrogen bond. Once you have hydrogen bonding opportunities in a molecule or interactions in a molecule, you will see that it's more stable, essentially. It requires more energy to boil. It requires less energy to do other things. It will more easily want to form a structured substance, but less easily want to form a unstructured substance like a gas. All right, so that's the main point here. So you're looking for nitrogen, oxygen, or fluorine bonded with a hydrogen, then you know hydrogen bonding is present in that molecule. Okay, here's a lot of information about water. You're more than welcome to go and read that up in your own time and think about why water then is such an effective controller of energy. I mean, we've spoken about why water, when you live near the coast, your temperatures are kind of mild because water absorbs a lot of energy during the summer months, so it cools down the area quite significantly, but it also then releases that heat during the winter months and it increases your winter temperatures then. So that's why your coastal climate is always kind of average. Versus, for example, tin foil that you take out of the oven, you can immediately touch the tin foil. There's no issue with you touching it because it has such a low heat capacity. It doesn't really absorb any heat. So the reason for water's high heat capacity is its hydrogen bonding. And I wrote the piece up there, so you can go and read. I don't know why I keep on doing that. You can go and read that piece there. All right. So now let's look at non-polar molecules. So what we've looked at ion with dipole. We've looked at dipole-dipole. So now what about dipole with induced dipole? So polar and non-polar molecules that we mix together. And the example here is one where we have water. So water is definitely a molecule with a dipole. And this molecule of oxygen does not have a dipole. And what essentially happens is if the water approaches the oxygen molecule, because this side is negative, so again, think of it as like a magnet, it pushes all the, I'm going to use a symbol rho, that's all the electron charge, it pushes that towards the right and induces a sort of a distortion. And by pushing all the charge to the right, it induces a polarity. So in other words, that we end up with a positive charge on the left because we've pushed away all the electrons to one side, and a negative charge on the right, so slightly negative. And then there's allowance for an interaction because one side is now positive and our water molecule is slightly negative. And that's why it's known as you have a dipole, so water, which then induces a dipole in a non-polar molecule. They're also called Debye forces. Peter Debye did some work on that. It's linked then to the polarizability of a molecule. So it means how easily can this happen to a molecule? How easily can its electron cloud be distorted? So it says basically an electron cloud of an atom or molecule with large extended electron clouds, such as iodine, can be polarized more easily than a small one, so like hydrogen. So the larger your molecules or your atoms are that the molecule consists of, your non-polar molecule consists of, the more easily it is polarized, and hence the more easily it has, or the stronger kind of dipole-induced dipole interactions it will have. Okay. Other indications, so we said larger. What is indication in chemistry of larger? It means the molar mass. So the greater the molar mass, the greater the polarizability of the molecule is. So that is polar with non-polar. What happens when we have non-polar molecules, two non-polar molecules? Well, in fact, they can also induce dipoles with one another, and we call them induced dipole forces. So it's sort of like peer pressure forces. These are also called London dispersion forces. I can't remember. London was a guy. It wasn't a place, just a place. This is a person. And what it essentially says is, let's say you have two nonpolar molecules. You have nitrogen, two nitrogen molecules. If those two nitrogen molecules move towards each other, there is on average, so this part isn't that important. So you have an averaging of the electron clouds. And on average, the electron cloud that moves in the one direction is going to be slightly positive, while the other one is slightly negative. And because your electrons aren't stationary, they move around in the molecule. So you can have a situation where, on average, all of these molecules seem nonpolar, but their actual interactions are that one side is slightly positive and slightly negative. And then they allow for a intermolecular interaction, which is then these London dispersion forces. So they are very weak forces. They're not the strongest forces in the group. They're the weakest forces that you get. But they also exist, and that's why we can, for example, get liquid nitrogen or solid nitrogen, because otherwise nitrogen would just never become, what do you call it, interact with itself to form a structured solid or liquid. It would have just remained a gas. So these forces are important for that reason. And interestingly, if you think about the logic of where they come from, so meaning that they are average of where the electron density is, and electron density, you can think of that -1 plus 1 is equal to 0, and 0 plus 0 is also 0. So on average, you can think of 0 as +1 and -1 kind of thing. Then it means all molecules must actually have London dispersion forces. The only thing is, non-polar molecules are so for non-polar molecules, they are the only intermolecular forces. So the only intermolecular forces between non-polar molecules. They are also present in polar molecules, but polar molecules can also have dipole-dipole interactions or ion-dipole or whatever interactions. So they will then have an additional force, and that's why they have higher boiling points, etc., than the non-polar counterparts. Okay. As always, with all these intermolecular forces, they increase with molar mass. So, for example, if you go from carbon to tin, you'll see that the tin has the highest boiling point and the methane has the lowest boiling point. That's why tin hydride is solid, and methane is a gas. Okay, so we're quickly asked to look at, suppose we have a mixture of solid iodine and the liquids water and carbon tetrachloride. What intermolecular forces exist between each possible pairs of molecules? So it basically means what happens if we place iodine in water and we place iodine in carbon tetrachloride. So what happens in either case? Well, iodine itself is nonpolar, right? So it's nonpolar. Water is polar. Again, iodine is nonpolar. And carbon tetrachloride is also nonpolar. So because this is carbon tetrachloride, it doesn't, it's nonpolar. So, question. On the left-hand side, we have nonpolar and polar. And on the right-hand side, we have nonpolar and nonpolar. So what does that then mean? Well, all kinds of things have London dispersion forces. So London, and this side also has London dispersion forces. Well, let's call them forces. Right, because both of those interactions will have this to some extent. The only question is, what are the other forces that can be here? And well, this is a non-polar molecule with a polar molecule, so it means the polar molecule can induce a dipole. So this one can have dipole, induced dipole forces, induced. And that's it. The other one cannot have anything else because it's non-polar molecules. Non-polar molecules cannot induce anything else except the induced dipole forces, which are called the London dispersion forces. So that's going to be the differences between the intermolecular forces happening with these mixtures. When you have polar and non-polar, it means you'll have London dispersion, but also dipole-induced dipole forces. Whereas if you only have nonpolar molecules, then the only thing there is the induced dipole, or otherwise known as the London dispersion forces. So typically, the question is, in which one will it dissolve easier? Well, it will dissolve easier in the carbon tetrachloride. And the reason actually is because of the addition of the other forces, but you don't really need to worry about that. Right. Right, so summary of van der Waals forces. So all intermolecular forces are van der Waals forces. We've discussed that. And it's interesting. The only thing that really I want to give you in this section is the summary of what all of them are. So as you can know, it's hydrogen bonding, dipole-dipole, dipole-induced dipole, or induced dipole forces, and what factors they depend on. So hydrogen bonding depends on an extremely polar XH bond, so that's why it's only fluorine, nitrogen, and oxygen. Very rarely is there other options, but for your purposes, you can remember there's fluorine, nitrogen, and oxygen. For dipole-dipole, it means there needs to be a dipole moment. So in other words, a polar molecule is usually a very good indication of that. For dipole-induced dipole, you need to look at the polarizability of a molecule. In other words, a large molecule, a heavy molecule, and is it connected with, you have a polar molecule and you have a non-polar molecule. And the non-polar molecule, depending on what its molar mass is, if it has a bigger molar mass, it's more polarizable than when it has a smaller molar mass. And then London dispersion forces just depends on the molar mass. So it doesn't really depend on if there's a dipole moment or anything because there isn't. It just depends on the molar mass. So Bromine will have a fluorine will have a lower boiling point than bromine, lower boiling point than iodine, and so on. Okay. And for example, geckos. The reason why geckos can climb onto walls is because they use London dispersion forces to um, climb up the wall. So I thought that was cute, so I included that. All right, so let's look at a nice concluding example for this theme. So we said identify the types of intermolecular forces that exist between each of the following. Molecules in liquid methane. So this is just liquid methane. So all we have is CH4. And CH4 is a nonpolar molecule. So if it's a nonpolar molecule, the only intermolecular forces that can be present is London dispersion forces. Or you can write induced dipole forces. B, we're told molecules of water and methanol. So water, so let's just draw water. Water we know is a polar molecule. There is a dipole moment. Oops, there's a dipole moment, definite dipole moment. More importantly, it's because the hydrogen is slightly positive, the oxygen is negative, slightly positive, so this is polar. And to that we add methanol, so that's H3COH. And this one we can also see there's a dipole moment. And even more importantly, there's some hydrogen bonding in both of these that can take place. So that bond is, we have a polar molecule. So the forces that are present here is we have polar OH bonds, right? So that's the first thing that we see. Polar OH bonds means hydrogen bonding forces. Other forces, so hydrogen bonding forces. Hydrogen bonding forces are a type of dipole-dipole forces. So you don't need to expand on that, but you can write dipole-dipole forces as well. Plus, there are, of course, always London dispersion forces. So that's the easy one. You can always write London dispersion. And of course, forces. Okay. And then the final one is molecules of bromine in water. So Br-Br plus OH. H2O, goodness sake. So bromine is nonpolar. Water is, of course, polar. So what are the things that are always present? London dispersion forces. London dispersion forces. And we have a polar molecule and a non-polar molecule. It means you have something that has a dipole, so dipole, which then induces a dipole. So dipole-induced forces. And they're also known as Debye forces, but Debye intermolecular forces. Right, so that's the basic idea of it. You have London dispersion forces in all of them. You can have dipole-dipole interactions, which extends to an extreme case where hydrogen bonding comes in. You can have a dipole interacting with an ion, so ion-dipole interactions, which we spoke about, depends on the size of the ion, the charge of the ion, and then finally you can get dipole-induced dipole forces. So where you have a polar molecule which induces a dipole in a non-polar molecule. Okay, and that's basically what you need to be aware of. You need to be able to identify those types in any kind of question example. If you're asked to give comment on why is the boiling point of this thing higher or lower, or why is its heat capacity large, or anything like that. Okay, I hope this was clear enough and not too boring, because this is just pure theory, so it can sometimes be quite tedious. But yeah, thank you for watching. Thank you for getting to this point in this video.